Imagine you're running a marathon. You high-five someone at the first mile marker and they see you as a human, normal. You high-five someone else at the 10-mile mark and now they see you as a panda. And when you high-five someone at the finish line, you're a honey badger. Bizarre? Yes. But this is the strange phenomenon called oscillation that scientists found in neutrinos. Much like a human suddenly appearing as a honey badger, neutrino oscillations were unexpected. They're proof that our understanding of the particle world isn't finished. So, today on EvenBananas, let's talk about how experiments study neutrino oscillation. As you can probably guess, neutrino oscillations are a major focus of research at neutrino experiments around the world. Some experiments study oscillating neutrinos from naturally created sources, like the sun or the Earth's atmosphere. We use particle accelerators to create a neutrino beam at Fermilab, to have a bit more control over the neutrino types, and an excuse to make pew-pew noises. At Fermilab, we have a lot of neutrino experiments that study how neutrinos behave over short and long distances. To explain how our experiments study oscillations at long distances, I'm joined today by Fermilab scientist Anne Nowrick. Anne studies... Anne, you know people are going to see this, right? What are you doing?
I'm oscillating! Hi friends, I'm Anne Nowrick and I also study neutrinos at Fermilab, which apparently means I'm not allowed to oscillate. I study neutrinos with the NOVA experiment and work with Kirsty on DUNE, which will make even better measurements of oscillation in the future.
When we try to measure neutrino oscillation, we're looking to see if the neutrinos change flavour as they travel. To accomplish that, some of our experiments use two neutrino detectors.
This means we measure our particle accelerator neutrinos just after we make them, in what we inventively call a near detector, to make sure we really know what we're starting out with. And then we measure them again at a distance to see if they have changed their flavor.
The NOVA experiment is making some of the world's most precise measurements of neutrino oscillation, using neutrinos from Fermilab's NUMI beam and a two-detector system. Roughly 1 kilometre away on the Fermilab site sits the NEAR detector, 100 metres underground. It's made of 300 metric tonnes of plastic, mineral oil and scintillator. Sections of it light up as particles interact in the detector.
The neutrino beam is very dense at the NEAR detector, so we see a lot of particle interactions. We collect data on their energy and flavor. The neutrinos that don't stop in our NEAR detector continue on about 500 miles up to the FAR detector in Ash River, Minnesota. The whole trip takes them less than 3 milliseconds.
Similar to a flashlight, the neutrino beam spreads out as it travels, so the FAR detector needs to be much bigger. NOVA's FAR detector uses the same materials, but weighs 14 metric kilotons and is about the length of a commercial jet. Making both detectors out of the same materials makes it easier for us to compare the neutrino interactions we see.
When the neutrinos get to Minnesota, we check to see how many of them have oscillated. At the NEAR detector, 99% of the neutrinos in our beam interact as muon neutrinos. But by the time they arrive in our FAR detector, almost all of them appear as electron or tau neutrinos.
And that's not a coincidence. We build our FAR detectors where we expect lots of neutrinos will have changed their flavour. In our marathon analogy, if you wanted to see a human change into a honey badger, and who doesn't, you'd stand wherever the math says is optimal honey badger zone.
It's very difficult for us to find tau neutrinos in our detector because tau leptons are really heavy. Most of the neutrinos in our beam don't have enough energy to make a tau lepton, so to us they're pretty much invisible. But NOVA can see electrons created by electron neutrinos that have appeared in the beam through oscillation. So that's what we look for.
One of NOVA's main goals is to see if neutrinos oscillate differently from antineutrinos by comparing measurements from a neutrino beam and an antineutrino beam. So far, there are some hints that they might be different, but we need a lot more data before we can be sure. In the future, we're planning to get loads more information about neutrino oscillation from the Deep Underground Neutrino experiment. DUNE is the next generation neutrino experiment that will be hosted at Fermilab. Like Nova, June will have a near detector located at Fermilab. That's the part I'm working on. And June's far detector will be 800 miles away at Ray Davis's old stomping grounds, what is now the Sanford Underground Research Facility in South Dakota.
Dune will have 4 far detectors, and each one will be roughly the size of the Nova far detector. These detectors will be filled with liquid argon, giving incredible resolution, so we can see the particles produced in the neutrino interaction to within a few millimeters. We're also building a completely new neutrino beam for Dune, which is going to be the most intense high-energy neutrino beam ever made. The combination of a really dense beam with enormous detectors means we'll get a lot of great data.
Thanks, Anne. I can hardly wait for us to learn even more details about what's really happening in neutrino oscillation. And who knows, maybe even discover why the universe exists. But I'll leave that for a future episode. That's it for today.